So yeah, welcome to the Machine Learning Tech Talks here at PicCollage. My name is Lawrence, for anybody who hasn't met me yet, and I work in operations. First of all, just thank you very much for everyone to coming here this evening. It's great to see such a thriving AI and machine learning community. So yeah, this is actually our second tech talk that we're doing here, and we're really excited and pleased to have two amazing speakers joining us this evening. We've got Annie, one of our very own machine learning engineers, who's going to be talking a little bit later on about GNN. And we've also got Thor over at the back there. You can say hello to Thor. Thor's going to be talking about, well, Thor's actually number one. He's visiting from Singapore. So it's really great to have him fly in for this. He's a software engineer at Supabase, and he's going to be talking about building AI applications with Postgres. Okay, so let's welcome in Annie.
Okay. Hello, I'm Annie, and I am a machine learning engineer in PicCollage. And today I'm going to share the sticker recommendation by Graph Convolutional Network. So here's the outline today. First, I will introduce what is Graph Convolutional Network and also some important concepts of the GNN. And then I will introduce the GCN, which is one kind of the GNN. And then is the model we used for our application called CompGCN. But I will not introduce very detailed, or I just say some contributions of this model and why we use it. And so the last part is how we do the sticker recommendation, what the idea is, and how we do experiment, and what kind of challenge we have faced, and then how to solve it. Yeah, so that's our outline. So first, the concept of the graph neural network is try to learn some mapping function to convert the discrete graph into the continuous space. The concept is that if you can see the different group of the color here. So if the nodes have many similar relations, the meaning is that they have common neighbors. They will be very closer in the learned vector space. So as you can see, the purple group will be very close when it converted to the output layers. Yeah, so this is the main concept we try to learn. So what is the input output? The input will be like two kind of graph. First one is undirected, and the second one is directed graph. So when we use directed graph, usually it's bidirectional. So we can predict both directions. And the output will be three different kind of level. The first one is the node level, and we can do some application like node regression and node classification. So for example, here we have a group of people. Some people will smoke and the other people don't smoke. So when we have a new person and this person have the relation between these people, already we know whether it is smoke or don't smoke. And then we can predict if these people smoke too, or how many percentage will he like to smoke. This is kind of application we can do. And the other kind of output will be age level. So it can be like age classification. For example, here is like e-commerce recommendations. So we can predict the relation between the product and the users. So for example, here if the people here, it's not okay. If the people they are like to buy the same thing, we can know whether you would like to buy this clothes too. So or if the two people buy the same thing, and if we can know maybe this is a product or this is the user. And another application will be like link prediction. So whether these two people will buy the same product. So by using these relations, and we can know the age, what is the age, what is the relation, and whether there will be a link between these two different nodes. And the last level will be the graph level. So this is kind of very few application using our list, because it just learned a representation of each graph. So usually it will be used like chemistry or like biological things. So Yeah, so we mainly use is like node level and edge level. And here is the first important concept of the GNN is whether this model is transductive GNN or inductive. So what is transductive? The model will embed all the nodes in a static graph, and the learned embeddings are used to predict the only existing the node in the graph. So if there is some new node that this model didn't see before, if we try to add this node in the graph, we need to retrain all the nodes. It is transductive. So in theoretically, this is practically is not good to use. Yeah, but inductive is in the other side. It can generalize to nodes that have not been seen before. And how we do this? It can generate the embeddings through the neighbors, and then it can get the new embedding for the new node. So if there is the new node coming, there's no need to be retrained. So here's an example. If there is already have these 3 different users, and we know the relation between each other. So if there is a new user 4, and we try to understand whether there's a link between the user 1 and user 4, we can use like, we already know that it's a link between user 3 and the user 4. So user 4, we can use the user 3 information to get the embedding of the user 4, so that we can use the embedding to predict whether there is a link between user 1. So this is the inductive version of GNN. And the second concept is very important, is how GNN do the back propagation. It will called a message passing. So for each back propagation, you will do one-time message passing. So there are 3 steps of message passing. The first one is the propagate. And the main idea is to get data. So you are taking the edge indices and all the additional data which needs to be constructed. And then the second step is message. You will construct the message for the node need to be updated. And then it's really take action. It's update. So you will update the node in the embedding for all the nodes in the graph. So it's like a cycle. First get the data and construct the message and take actions. So you will use this way to update all the nodes in the graph. So here comes a new one kind of the GN called Graph Convolutional Network. So the reason why it called Graph Convolutional Network, because it used the concept of the convolution. But here it's not the same as the CNN. It just borrowed the concept. So imagine like the node is like the pixel. And if there is the relation between the nodes, means they are very similar. So this is kind of concept in the pixel, like in image. If the pixels are very close, they may have the similar features. So they use this kind of concept to do the convolutions. And so when we try to get the red node, we will do like average, weighted average sum or some operations. Use the neighbor's information to get the entire information of this part of the nodes. So we use this model called CompGCN, which is a paper in ICLR. And why we use this? Because it has many good parts. The first good part is it can use to embedding both the node. It can get both for the embedding for the node and the relations. And because it uses composition operations, so it can take less of time to do the time message passing. As you know, if the graph is very big, like knowledge graph, there must have many informations, so and then many nodes. So but he used composition operation to make the message passing faster, and also the performance is very good in many different applications like node classification, link prediction, and graph classification. So we use this because it's very effective and also the performance is very well. So here comes the applications. It's called sticker recommendations. So the problem we try to solve is when the user input one or some photos, they don't know what stickers are suitable to use. And we have so many stickers in the app, so usually the user cannot go through all the stickers. So we try to recommend stickers that are related to their photos. So the main idea of our solution is that similar photos will use similar stickers. And stickers that are often used by some photo or have similar attributes are relevant. So we use this kind of concept. So for example, if the dog in the photos, we imagine that user might want to use the sticker like bones. And if the image is like cat, they might be like to use the paws. So by using this, we can, we think it's very similar of the concept of the GNN. So we use CompGCN to solve this problem. And we use the link prediction. So model can know whether there will be the edge between the two nodes. The nodes will be photo or stickers. So when input an image, we will know whether the stickers, the circle is an image, is a stickers. So we try to predict whether there is a link between the stickers and the photos. So here's more clear what we input, what is the output. So input will give in one or more photos, and we will use the model called clip to get an image feature of each photo. And then if we have more than one photo, we will just average it. And finally, we can get one embeddings and put into the graph model and do the link prediction. So we can get top n sorted by the scores, and we can choose like top 10 stickers and then recommend them to the users. So the data. So I'm going to explain the experiment. The data we use is from the users collage. It's about 20,000, and the node only has two different kind of nodes, which are the follow and the sticker. And the relations, we only define one is use sticker. So as I said, because it's a directional graph, so we have the opposite one. So be used by is also a relations. So as you can see, the label will be like this. The green will be the photo will use the stickers. So also the stickers were used by these photos. So there are some challenges we have faced. The first one is how we deal with the new photos. So because this model originally is written in transductive, but it is not official for our application. So because we cannot do every time we need to retrain when there's a new photo, it's very impossible for us. So we need to transfer it into inductive. And by how we do this, we just adding one layer after the clip vector. So we will learn the weight of this layer so that the model will be inductive. So by doing this, we can have dealing with the photo that haven't been seen before and no need to be retrained again. And the second thing is how we deal with the new sticker. The concept is that we need to add the relations between the nodes that already exist in the graph between the new stickers. So how we add these relations? We just input the opposite one. We will input the stickers, and we will use the prediction, a link prediction, and we try to predict whether the photos were used by these stickers. So we can get like top 20 or top 40 photos that might use these stickers, and then we can get this relation to be our level, so that we can add the new stickers into our graph. So as you can see, if we input these stickers that they have hearts, so we can predict like this. These photos will use these stickers. So these photos is like couple related, and these stickers is like Christmas. We will give them like Christmas related photos. So here's the result. But if we input the photo, and the model will output like this. So for example, here is like people in the party will give like live happily, or like a camera or some sunshine like this. And if we input like the pets, we can have a cat or some paws and some coffee, maybe just like very chill and happy. And for baby, we can have some cute stickers. So here are other topics, like for beach, we can have some like camera and some sunshine like here. And Christmas, we have Christmas stickers, and also wedding and Halloween. So overall, we think the performance is quite well. So yeah, it's almost it's my presentation. So thank you for attention.
Is this clear?
Yeah.
Because I think your architecture, you use clip to extract the feature from the image. And I think people know that the clip have two drawbacks. The first one is it is hard to handle out of distribution data. And the other one is it is hard to encode spatial relationship. So did you encounter any problem about this too?
I think because we use clip just for initialize the node embedding. So the how we update the node embedding is use our like messenger passing. So although there's maybe some flaw about the clip, I think it's not so important about, because eventually we'll use the data to learn the embedding and learn the nodes. So the clip, I think, is only the initial for the for the start. Yeah.
Okay. 大家好，我是雷神，可是台风跟我没有关系。Okay, that's unfortunately where my Mandarin stops. Yes, I'm Thor. For the others who didn't get my joke, I don't have anything to do with the typhoon. It's just a nickname. Yes, I help developers build. So I'm a software engineer myself. I work for a fairly young company called Supabase. Actually, can I get a quick show of hands who has heard of Supabase? Okay, not too many, couple folks, that's great. So Supabase is an open source alternative to something like Google Firebase, but it is built on top of Postgres. So relational databases, Postgres, probably one of the database has been around for 30 years, likely a good choice for 95% of the applications you're building, except if you're building rate limiting, then not the best choice, but there's other solutions for that. And what we do is we build an entire backend stack on top of Postgres. So we give you a fully fledged Postgres database. On top of that, we give you an authentication server. The authentication server itself uses the Postgres database, just a separate schema within that to manage all the users. That's an open source project called GoTrue, originally built by Netlify. We forked off of that and are contributing to that. We have a file storage for anything that's sort of unstructured data, video, audio, images, what have you. We have edge functions. So, if you're building a mobile application and you need to process, some requests, a good example for that is payments. For payments, you need some secure server-side environment. So you can use edge functions, and we're using Dino, a Dino edge runtime here. Again, we chose Dino because it is fully open source, so we can have the same experience locally as deployed. And we try to have everything open source and portable. That's kind of our idea. So every piece of this stack you can run on its own. So you can only use the authentication part, only the edge functions, what have you. You can actually take it and host it yourself since it's open source. So that is something what a lot of people appreciate is sort of, you can get started quickly. That's kind of our tagline, built in a weekend, scale to millions. but you have sort of that confidence that a Postgres scales with you, and also should you want to, you can take all of it and host it yourself. Yes, we got another couple of things. So real time is, if you're familiar with Firebase, you generally use it for kind of real-time applications, things like chat applications, where you kind of need to sync a couple of clients in real time with that new information. So again, we're using kind of the power of Postgres here. We're really sort of standing on the shoulder of giants with Postgres, which is very powerful. And actually, our real-time service is an Elixir server that is running off of the Postgres replication stream. So Postgres has built in kind of this replication stream that any time there's an event kind of in a table, there's a new row inserted, there's something updated, deleted, there is a replication stream. And basically, we have this Elixir server that is listening to that replication stream and then is broadcasting that via WebSockets to the connected clients. And oh yeah, one other thing that's pretty handy with basically every piece of the stack integrates with each other. So the authentication piece works with the database, and you can actually basically restrict data through something that's called row-level security that's built into Postgres. And you can utilize the JWT that you get from the authentication service to restrict kind of the data. And actually, that allows you to directly communicate with the database from your client application. So that's another big piece, right? From Firebase, you can use your mobile application to directly talk to the database. You just need to understand how Firebase security rules work. So we have kind of RLS, which is security rules in SQL, not necessarily an easier experience, but we're trying to make that kind of easier. But so with that, we actually give you an API to directly communicate with the database from your client. So when you're building mobile applications, you can do that securely without kind of leaking, data that shouldn't be read by other users. So every part of the stack is portable, but integrates kind of nicely with itself. For like file storage as well, you can use the same authentication system, the same row-level security policy system to restrict access to files in kind of your storage. And so same with edge functions. You can get the user context of whoever invoked the edge function, and you get the idea, right? And the last piece, which is kind of a fairly recent addition, is sort of vector databases on top of Postgres. In the first talk, you've heard about embeddings and generating vectors, and you need to kind of store these vectors somewhere and query them. And generally, that's something where you perform kind of vector similarity search or proximity search, you can call it. So kind of find the vectors that are closest to each other, which sort of gives you the idea of the context. And so Postgres has a great extension ecosystem, and we're using an open source extension called pgvector to facilitate kind of these vector mechanics within the database itself. So I have kind of some resources I'm using in this talk. So if you kind of want to take a note of that, you can scan the QR code. You can go, this is the URL here, thor.bio. I tried to get thor.dev as a domain, but some guy somewhere in Canada is sitting on that, and I haven't been able to make contact. So it's not in use, but I used to have thor.news. And I always thought, oh, Marvel is going to approach me one day and give me a lot of money for that. Didn't happen. So now I got Thor.bio. Anyway, yes, first of all, thank you for PicCollage for hosting us here today. I've actually been able to work from this office for the last couple of days, which was really nice, and get to know the team better, which has been great. So thank you very much. Okay, so we have a couple of resources here. We can start if you kind of want to understand sort of the, what are embeddings, what is Postgres, kind of pgvector, how do you store sort of vector embeddings in your database. We heard about this a little bit already, but maybe we can dive into sort of how do embeddings work. So it's sort of this idea where you take something like human language or images, and you turn them into kind of vectors. Somewhere, this is just a two-dimensional representation. But the idea is that you basically take the context of what you have here. So the cat chases the mouse, the kitten hunts I have actually no idea what that says. But the idea is that, the cat and kittens contextually quite similar. So you see that the vectors here are fairly close to each other. Now, then you have something like, I like ham sandwiches. Doesn't really contextually, ham, cats, doesn't really contextually work together. So the vectors are fairly far apart. That is kind of the general idea with sort of the vector embeddings. And you basically take this human kind of context, say human language, images, human vision, and you turn it into these vectors. But rather than 2 dimensions, you have more than 500 dimensions to actually sort of make the context of something like human language work. And then what you can do is basically pgvector allows you to store these big vectors in your Postgres database and create some indexes on it for kind of performance improvements, and then perform kind of this vector proximity search. And let's actually do that. You can dive kind of into the docs a bit more here. There's a bunch of examples we have, but one example I want to show is this, and this is actually using the same model as earlier. It's using the open source OpenAI clip model. It is using an open source wrapper here that is called sentence transformers, I think, yeah, sentence transformers. And basically what this does, it translates both images and text into the same vector space, which means that you can take the context from an image, like here, 2 dogs in the snow, as well as the context from the language, in this case, English, 2 dogs in the snow, and you see that these vectors are very close to each other. And you can imagine what you can now do with this is basically, image search. You're probably very used to that. You use your Google Photos or your, what have you, competitive product, and you put in me on a bike, and you get all the pictures of yourself on a bike. But how does the technology behind that actually work? And so this is something where you can do that. You have the text and the image in the same vector space. And so I have this example here. And what I can do is I can start Supabase. So that's the entire kind of open source Supabase stack. And I can run it locally on my machine. And this is kind of everything. So it does require Docker. So you can see that here. It spins up kind of a whole sort of stack of Docker images. And then you have here like your database URL, which is like the Postgres database running locally. Your REST API, we generate a GraphQL API. And then also we have a studio, which is kind of a dashboard on top of your project. And so this is sort of your project locally. You have kind of different schemas sort of in here, as I mentioned, sort of auth, extensions and all of that. And now what we want to do is actually we want to generate kind of these embedding vectors. So let's look at the code. The code is actually fairly straightforward. So with Supabase Vector, we have a Python client SDK. It's called Vex. That sort of takes care of kind of all the stuff in the background that you need to do, like setting up the schema, enabling pgvector, sort of creating database functions to perform kind of the similarity search. So you don't have to worry about that. That's kind of packaged within sort of this client. And then we just have a method here where, you remember this was kind of our local database URL. We have a seed method where we're basically just using Vex. We're creating the client to our database. We're creating a collection. We call it image vectors. We need a dimension 512. So you're, pretty decent sized vector. And then we're using this here, the sentence transformer, which is the OpenAI clip model. And then we just have some images here. These are just open kind of images from Unsplash. You can remember kind of what we have here, so we can demo this later. So we're encoding these images into our vectors. And then what we can do is we can just upsert them into our collection, into our database. And then we're just printing, OK, inserted images. We're creating an index so that querying later, specifically for that proximity search, is fast. And yeah, let's actually do this right now. I need a poetry shell. I'm just using poetry here for kind of dependency management. And then I can say poetry run seed. And so now we're turning all these images into our vectors. You can see we've inserted the images. We've created our index. And so now when we look here, I might need a bit to refresh. We now have a new schema called vex. Image vectors, and here we have all our images, and these are our big, long vectors that represent kind of the context of these images in our database. Okay, so now that we have sort of the context in our vectors in our database, what we can do is we can perform a search. Again, we create a client. Now we already have our collection, so we just get a kind of an instance of our vex collection here. Same model again, the clip model, but now we're encoding our query string into an embedding in the same vector space. And now we can just run a query with our text embedding vector. We can say limit 1. So basically, we just want the most relevant result of the search. And then we have some sort of metadata filters that we can put in that are just kind of filtering down the data set beforehand. OK, so what do you want to search for? Anyone remember the images we had? Grapes. Yeah, grapes is a good one. OK, let's see. So if everything goes well, there we have it. Grapes. Great. What should we try again? And I just named these as like 1, 2, 3, 4, just to show you I'm not cheating. There's no context in the name of the file or anything, or some maybe something more abstract, more challenging, which maybe is a bit further away. Maybe fruit, right? There was no other fruit kind of in this collection. So fruit itself will likely be a bit further away from the vector, but it's still the closest to that image of the grapes. We had maybe bike. Yeah, we didn't really have anything closer to a bike, right? So we get kind of the bike in front of the red brick wall. But yeah, you get the idea. We're taking kind of our text and we're sort of contextually comparing it to, OK, what's the closest image we can get for this text? Now, another thing, because we have this shared vector space, we can actually use the input of an image itself, right? And so that's kind of the Google reverse image search. You take an image, you turn it into a vector, and then you query, OK, give me all the images that are similar to this image. Now, I haven't implemented this in the demo here, so that's your homework. When you go home, you can clone the demo, you can open the PR. It's all open source. Lovely. Yes, so this was example number 1. Let's just tear down the Supabase stack here. And then we have another example that's here actually using, so this was kind of a Python example here. We also have a TypeScript example, sort of building your own ChatGPT. Now, this is basically just using the OpenAI text completion API, which is sort of the concept of ChatGPT itself. But what we're doing is we're injecting context of our own documentation. And if you look at this here, we actually have this in our docs. So that's kind of how it started. It was sort of an experiment in our docs where I can say like, okay, how do I build my own ChatGPT? And then now we're turning this query into an embedding, into a vector. We're looking up in our database any documentation that is relevant to this query, and we're injecting that context into our text completion prompt. Now, maybe this is a bit abstract, but you can see we're then kind of streaming the response from ChatGPT. It's not, not always great. It's experimental, but let's have a look quickly what that looks like. Code. Let's start up our Supabase stack locally. So I can show you, I have kind of a local sort of seed script. So basically what we're doing here is we're taking all the content that is in our pages. So say you have a product where you have documentation. You oftentimes write that documentation in Markdown files, right? So for example, all our Supabase documentation is in Markdown. And what we do is we have a script that's here. Where is it? To somewhere. Library. Generate embeddings. So this script we basically run anytime we make changes to our documentation. We break down kind of our docs into different sections, and we generate embeddings for all that text, and we store it in the database. So what that looks like kind of in the database itself. So this is now our other local project. So we have kind of our pages here, docs, OpenAI embeddings. So that's our page here, this one, OpenAI embeddings. And then we have this sort of page section, which is kind of all the different sort of headlines. So we break down the documentation, and again, we generate kind of a vector embedding here. In this case, we're using the OpenAI API to kind of generate these embeddings. And then what we can do is we can perform, again, kind of a vector search on this. Let me see. So we have here this vector search sort of edge function. And we can quickly step through. So we're using kind of GPT-3 here to create our embeddings using sort of the OpenAI API. So our query, and then we're performing here with JavaScript. So it's kind of the same query, but we're using a remote procedure call, kind of an RPC database function via sort of the REST API, and we have that. We can use that in JavaScript, and then can kind of, sort of narrow down that search here, the thresholds. We're tokenizing that, and then what we're doing is we're getting basically all the page sections that are relevant to the user's question, and we're creating our prompt. And so our prompt basically says, you're very enthusiastic Supabase representatives, loves to help people. It's always good to tell OpenAI to be friendly and helpful. Otherwise, you never know what comes out. And then given the following sections from the Supabase documentation, answer the question using only that information, output it in Markdown format. And so this is kind of the relevant piece where rather than OpenAI going off and taking all the public information out there, we're actually narrowing it down to the context that we have in our own documentation. And then what we can do is we can inject that context, and we can provide our question, and then we're streaming down the Markdown. And I'm running out of time. So npm, I think it's actually pnpm run dev. Let's quickly do this. Okay, very quick. So for example, if I ask here, what are embeddings, right? And this is just basic ChatGPT, you know, the one that's available to pretty much everyone. And then it goes off like, oh yeah, so in natural language processing, machine learning, yada, 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 right? So in our case, we're injecting some context into the search. And so now if we say here, what are embeddings, we get a more kind of concise answer that is actually sort of relevant to our context. Because, you know, we know they are asking this in the context of Supabase. We then kind of inject the correct context. Another one that's maybe, yeah, so you see kind of how, okay, this goes off. It needs to say, okay, in machine learning world, blah, blah, blah. We can do, can we store embeddings with Supabase? Question mark. And so what this now says is it actually introduces Supabase first, yeah, open source. You know all of this, right? You're looking for this in the context. But now the interesting thing is actually it recommends you to use a float, an array of float, right? Rather than actually the vector that is optimized for vector search. So by basically injecting the correct contents, can I store embeddings with Supabase? We can now basically make sure that we're actually returning the correct context. And we've injected, okay, pgvector is what we use for embeddings, for storing embeddings, for performing kind of the similarity search. We actually get a way more precise and concise answer. Yes, and I think I've been speaking way too long, but thank you very much for giving me your time. Do follow us on Twitter mainly, star us on GitHub. I think we're getting very close to the same star count as React.js. No, very far away, but still, yeah, if you haven't heard of it, check it out. And thanks so much, and let me know if you have any questions. Cheers.